Probability by Ted G. Lewis. Humans have been interested in this question for a very long time, going all the way back to antiquity. For example, the ancient Greeks asked Pythia, the oracle of Delphi, to tell them what was going to happen in the future. Could they win wars? Was there going to be enough food? Etc. But it was nearly 2,000 years before the scientific study of the future, called probability theory, was discovered and developed during the Enlightenment. Blaise Pascal is credited with inventing modern probability theory in 1654. More recently, some people claim that Google Trends is an indicator of the present, and possibly the precursor to the immediate future. But that's another story. There are many barriers to prognostication. First and foremost, is it even possible to predict the future? This philosophical question will remain unanswered for now, but I will admit that it is currently impossible to predict the future with 100% reliability. However, we are able, as a society, to predict the most likely future based on current conditions and knowledge of history and science. This is, of course, the purpose of probability, to estimate the likelihood of various futures. Even so, there are other barriers to estimating the likelihood of future events. For example, the famous Heisenberg uncertainty principle introduces uncertainty into measurement because the mere act of measuring something changes it. And then there is chaos, the nonlinear behavior of complex systems. Most predictions assume a linear relationship between now and then, but chaotic systems behave erratically, introducing unexpected non-linearity. Even a very small change can lead to a radical departure from the status quo. Nevertheless, we can make accurate predictions of things to come using probability theory, most of the time. What is a probability? In the simplest terms, probability is a measure of uncertainty. It is also a measure of certainty. How can it be both? First, probability is a number between 0 and 1. If the number is 0, we know for certain that the event will not happen. If the number is 1, we know for sure that the event will happen. 0 and 1 both represent certainty. A number in between 0 and 1 is a measure of our ignorance about the future. The closer a probability is to 1/2, the more ignorant and uncertain we are that the event will happen. Maximum ignorance, and therefore maximum uncertainty, occurs when probability is 1/2. We can write the probability as a fraction, 1/2, a decimal, 0.5, or a percentage, 50%. The use of fractions and decimals to measure uncertainty is not an artificial coincidence. It is by design, because the probability of two independent events, A and B, happening together is smaller than the probability of either event happening independently. We calculate the joint probability by multiplying the independent probabilities together and noting the result is less than either one. This is only possible when the independent probabilities are numbers less than 1. That is, decimals get smaller when they are multiplied together. Here's how it works. Suppose we either toss 2 coins at the same time, or toss 1 coin twice and record the results. Each coin turns up either a head or tail. Assuming the coins are fair, and so is the toss, the probability of turning up heads is 1/2, or 50%. The probability that both tosses produce a head is the product of the independent probabilities. Thus, 1/2 times 1/2 is 1/4, or 25%. Why? This table enumerates all possible outcomes from tossing 2 coins. As you can see, there are 4 outcomes or combinations. Note that there is only one outcome of the 4 possible outcomes that matches the desired future, head and head. Thus, the likelihood of 2 heads in a row is 1/4. This means that in the future, whenever a coin is tossed twice, or 2 coins are tossed together, the likelihood of 2 heads occurring is 25%. In other words, it isn't very likely, but at least it is just as likely as any other combination. This illustrates one method of calculating a probability, the a priori method. In the previous example, the probability of getting 2 heads in a row was calculated by considering all possible combinations. This is one way to predict the future, but there is another way. A second method, called the a posteriori estimate, is to consider what has happened in the past and use it to predict the future. The a priori method is purely mathematical, while the a posteriori method is purely experimental. One requires mathematics, and the other requires careful observation and measurement. For example, suppose we toss a pair of coins 408 times, and record the results in the form of a histogram as shown on the right. 0 heads appeared 103 times, 1 head 207 times, and 2 heads 98 times. Dividing 98 by 408 gives us an estimate of how many times 2 heads will occur in the future. In this case, the estimate is 0.24, or 24%. So we should expect 2 heads to occur 24% of the time in the future. Why are the a priori and the a posteriori estimates different? The answer: if we keep tossing the coins long enough, the difference will disappear. This is called regression to the mean, or the law of large numbers. It says that if we do enough experiments, the a posteriori probability will equal the a priori probability, but we may never have enough time or data to make the two come together. So we accept a certain amount of experimental error. How do we know when we have enough data to trust the a posteriori estimate? This is the field of study called statistics, which is beyond the scope of this lecture. As an illustration of how to calculate an a posteriori probability from history, consider the problem faced by Simon Pierre Laplace in the early 1800s. Laplace was asked to calculate the probability that the sun will rise tomorrow, given that it had appeared in the past. He used a posteriori estimates as follows. The number of times the sun has risen in the past is a very big number, and so is the number of days in the past. Add 1 to this number and divide the sum by the number of days in the past plus 2. You get a number very close to 1. That is, the chances of the sun rising tomorrow is very good indeed. Laplace's formula can be used to estimate the a posteriori probability of other events, too. The formula is 1 plus r divided by 2 plus s, where r is the number of times the favorable event has happened in the past, and s is the number of times both favorable and unfavorable events have happened. Coins have 2 simple possible outcomes. That is, each coin-tossing event produces either a head or a tail. What if the event is much more complicated, so that an array of possibilities are likely? This situation requires a probability density function, or histogram, to represent all possibilities. In the real world, there are many possible outcomes and their corresponding probabilities. Here is an example. You have already seen one example. Tossing 2 coins and recording the number of heads produces multiple outcomes. What if we tossed 3 coins, 4 coins, 5 coins? After a while, it becomes difficult to keep track of all the possible outcomes. For example, the histogram shown here lists all the ways of obtaining heads by flipping 5 coins. This histogram is a probability distribution function. It plots the probability or frequency of an event along the vertical axis, and the value of the outcome along the horizontal axis. In this example, the probability of 5 heads from tossing 5 coins is 1/32. This distribution has a name. It is called the binomial distribution because there are only 2 choices for each coin. As the number of possible outcomes soars and becomes even too big to count, the binomial distribution turns into the normal distribution. You can think of the normal distribution as a kind of infinite binomial distribution. The bars of a histogram melt into a smooth curve, as shown here. Notice a couple of other properties of the normal distribution. First, it has an average value, and it is symmetric around this average value. The likelihood of an event falling below average is equal to the likelihood of it falling above the average. Second, probabilities fall off quickly on either side of the average. How fast they fall away is measured by the standard deviation of the distribution. A low standard deviation means the distribution is narrow, while a high standard deviation indicates a fat or wide distribution. A wide distribution usually indicates greater uncertainty. A big difference between the binomial and normal distribution is in the number of possible outcomes. As the number of outcomes along the x-axis becomes infinite, too many to count, the likelihood of each outcome actually occurring vanishes to zero. This seems to be a paradox. How can the likelihood of an event vanish even as the number of occurrences of that event increases? This is the basis of the calculus, which we defer to another time. But for the current discussion, the vanishing probability problem is handled by using intervals in place of points. So we ask, what is the likelihood that a molecule occupies a box in space? Or, a student test score falls in the interval of 90% to 100%, or below 50%, or above 70%, and so on. By using intervals, we get around the vanishing probability problem. Let us turn now to what insurance companies and disaster analysts call exceedence probability. It is used to estimate the likelihood of something of a certain size or bigger happening. What is the probability that your height is greater than the average height of all humans? Because the normal distribution is symmetric around its average value, we know the answer. You are 50% likely to be taller than the average person. This is shown here by an interval along the x-axis of the normal distribution. The area under the entire normal distribution is equal to 1, so the area under 1/2 of it is 1/2, or 50%. In many cases, we are interested in whether or not an event is at least as big as a certain size. This is called exceedance. If there is some uncertainty in the value of exceedance, we call the prediction an exceedence probability. And finally, if there are many possible exceedances, we use an exceedance distribution to record the array of possibilities. Exceedance probability curves are known and used to gauge likelihood of hazards such as earthquakes, floods, and hurricanes. The famous Richter scale for earthquakes is a measure of disturbance based on the 1% probability level taken from the exceedance probability distribution for recorded earthquakes. Hence, it is an a posteriori estimate. Similarly, the severity of floods and hurricanes is obtained by assuming a certain level of likelihood. For example, the well-known 100-year flood is a flood of such severity that it occurs with probability of 1%. That is, the a posteriori probability of a typical 100-year or more flood is 1%. Wind severity is based on the 500-year event. A once every 500 years event is 1 out of 500, so its probability is 1/500th, or 0.2 of 1%. Thus, the probability of a 500-year hurricane is very small, but its impact is very, very large. In many cases, disasters such as earthquakes, hurricanes, terrorist attacks, and casualties in wars obey long-tailed distributions like the ones shown here. They are called long-tailed because they are lopsided. The most likely events are small, as indicated by a higher probability on the left. The worst events are rare because they occur on the right, or the so-called long tail. These events are also called black swans, after the name given them by Taleb in his book by the same name. Of great significance is the fact that long-tail distributions have no average value or standard deviation. Thus, they describe events that are atypical or non-parametric. Some long-tailed distributions are famous. The Pareto distribution for wealth says most people are poor or middle class, and only a very small percentage of the population is rich. The Pareto law is also known as the 80-20% rule, because the first 20% of the events account for 80% of the probability. These distributions all belong to the same class of distributions called power law distributions. Power laws describe most disasters, catastrophes, and terrorist incidents, so I will constantly refer to them. Given a distribution of like events, we can calculate risk. There are two definitions of interest to this course. The first definition is based on expected utility theory, which says risk is expected loss. We call this simple risk, and calculate it by simply selecting a point on the x-axis of a distribution and multiplying it by its probability. Thus, simple risk is the product of probability of event x times the consequence of event x. Another definition of risk used by the casualty insurance industry is called probable maximum loss, PML, and it measures the risk associated with exceedance. In this form, risk is the product of exceedance probability times the consequence of event x. Typically, PML risk is obtained by multiplying the vertical and horizontal axes of the exceedance distribution. For example, the white curves shown here are PML risks obtained by multiplying vertical and horizontal axes together. Note that in one case the risk curve continues upward as the consequence increases. This is called a high-risk hazard because risk increases with consequence. In the other case, the risk curve rises but then declines to zero as consequence increases. This is a low-risk hazard because risk diminishes with consequence. PML risk is a measure of the worst-case future. It is typically used to estimate the risk associated with natural disasters like hurricanes and earthquakes. One more thing. In the foregoing, we assumed events are independent of one another. In reality, most chance events follow from previous events. That is, the likelihood that event B will happen is conditional on the likelihood of a previous event A already happening. For example, the likelihood of the nuclear reactor at Fukushima being damaged by a tsunami was increased by the fact that an earthquake happened prior to the tsunami. Thus, most probabilities are actually conditional probabilities. The probability of event V depends on the probability of event A. When we already know that A has happened, it reduces our ignorance and therefore reduces uncertainty. As we reduce uncertainty, we reduce the space of all possible outcomes, as shown here. This is the essential property of conditional probabilities that make them different from independent probabilities. Remember the coin tossing example given earlier? What is the probability of both coins turning up heads if we know for sure that the first one is a head? The fact that the first coin is known to be a head reduces our ignorance, and therefore reduces uncertainty. This means the number of possible outcomes is also reduced, as you can see from the table. So the probability that both coins turn up heads is conditionally 50%. We say the probability of getting a second head, given that the first coin is a head, is 50%. We say a probability is independent if its value is independent from all other events. We say it is conditional if some other event can change it. As an example of the application of conditional probability, consider the following hypothetical problem. What is the probability of someone in the U.S. being killed by a terrorist? This problem is more complex than I have made it here, and in fact, a variety of estimates can be found in the literature. It all depends on how you define the space of possible outcomes. An overly simple answer is to divide the number of deaths by the total population. Doing that gives you 1 out of 30 million as the likelihood. However, this assumes a uniformity of people, places, and temptations of the terrorist. A somewhat better estimate, but one with many problematic assumptions, is as follows. The probability of a successful attack is equal to threat, T, times vulnerability, V. Suppose we assume total ignorance about the intent and capability of all terrorists. Thus, the probability of an attempted attack is 50%, our measure of maximum ignorance. Next, suppose we use a posteriori estimates to get the probability of success given an attack takes place. Since 2001, there have been 26 attempts and only 3 successes. Therefore, I will use the a posteriori estimate proposed by Laplace in the 1600s. 1 plus successes divided by 2 plus total attempts to get 4/28 as my estimate of V. Multiplying these together, the likelihood is approximately 7%, much higher than 1 in 30 million. So, what have we learned? First, probability theory is used to assess the future. It is a measure of uncertainty and a measure of the likelihood of events occurring in the future. There are two kinds of probability: a priori, for estimating using mathematics, and a posteriori, for estimating the future from observing the past. When the outcomes are many, a probability distribution is used to show the relationship between events and their likelihoods. The normal distribution has an average value and standard deviation. Significantly, power law distributions have no average value and no standard deviation. This has a special significance in disaster prediction. A hazard that follows a long-tailed power law has no typical case. That is, the worst case is unbounded, while at the same time most events are of low consequence. Simple risk is defined as the expected value of an event. We use it here to estimate the expected loss due to some disastrous event. PML risk is the product of exceedance probability times consequence. Its advantage over simple risk is that we can classify hazards according to whether they are low or high risk. Exceedance probability distributions are useful for estimating the worst-case events, because an exceedance probability distribution measures the likelihood of an event of size x or greater. Exceedance probability distributions are used in calculating PML risk, and of course, PML risk is the risk associated with worst cases.